All footage used in this video is gonna be recorded off of a real N64. Before I start this video, I want to clarify. The devs back then couldn't possibly have done all these optimizations. The understanding of the hardware wasn't as ripe as it was a few years later, and the fact they even managed to program all this math to make a 3D game work in the first place is already pretty damn impressive. That being said, there were many silly and uneducated decisions in this game that made the render incredibly slow. A lot of these optimizations I'm talking about will also apply to modern game development. However, CPUs nowadays are so fast that devs don't really care about these optimizations anymore. And it's why we get so many poorly optimized games nowadays. I want to clarify that here I'm talking about the graph building code, not the actual pixel output code. Those are two separate components that can each slow down the FPS of an N64 game individually. Before any optimizations, using the default Super Mario 64 compiler, this level with assets would have taken around 28 milliseconds to render. That means we could render the level around 35 times per second. However, we also have to calculate in time to process the entire game, the physics, the objects, all of that, which leaves almost no room for us to actually render the frame, and it would seriously tank the FPS. Using modern GCC and O2 optimization, we can run the code much more efficiently and bring the time to render the frame down to 23.5 milliseconds. These are 4.5 milliseconds we get simply for turning on compiler optimizations. This could have been done back then too, but they didn't. Funnily, I have actually asked Goddard, a Mario 64 dev himself, as to why this would have been the case, and he theorized that it was because they didn't want to risk the release version having any bugs that the debug version did not have. Originally for this chapter I had a long section planned where I would explain all the code. However, while editing it, I realized that this probably bored the hell out of all you guys, so I'm just gonna put a little montage. There is an explanation for each one of these functions at the very end of the video, and doing all of these saved us around 3 milliseconds of render time, meaning we're down to 20.5 milliseconds. Next, and this was an incredibly stupid issue, but when I looked over the code, I saw that Mario 64 did 3 vertical raycasts, just to find the position and slopeness of a floor below an object to draw a shadow. Why 3? Well, this was just incredibly stupid and awful, and it's pretty much inexcusable. Whoever wrote that at Nintendo back then, I hope Miyamoto is still scolding him to this day for that. It doesn't do this to get better coordinates or anything, it's literally just stupid. Fixing this was pitifully easy and an insane speed up. Reducing this to a single raycast brought the render time down to 17.5 milliseconds. Which means we now can process 56 frames every single second. At this point in my journey through optimizing Mario 64's render graph, I thought I couldn't do anything more. But oh boy, was I wrong. Before we get into the next part, I also want to mention that O2 does not help anymore. Every time I upload something related to optimizations, I got comments asking about O2. The original Mario 64 was compiled with no optimizations, I get it. But I'm already 2 optimizations levels ahead of O2. I'm using OFast, which is significantly faster than O2. All these code gains I am talking about were made after the game was already OFast compiled, meaning you cannot further improve it with O2. In fact, it would be worse. So after all these optimizations, what else did I find? I looked at the entire codebase with what I had learned in mind, and I redid pretty much the entire graph render code outside of the math. Most of the speed up was from taking better advantage of the instruction cache. And now that I've done that, the code is not only more practical to work with, but it also only takes 14.9 milliseconds. Which means that now technically we could finally process more than 60 FPS. In the Mario 64 modding community, we use a Blender add-on called Fast64 to make our 3D models. This modding key model here is ripped straight from Mario 64. And as you can see, it has a lot of useless bones that do nothing. Unfortunately, I have absolutely no possible idea on why they were added. I collaborated with the Kaze, the FAST64 developer, to work on a more efficient geo-layout comment structure to make this work even better. Unfortunately, at this point I have added other details to the level that make these next numbers a bit inaccurate. But with the new comments and unnecessary animation bones removed, we now drop down to 13.4 milliseconds. I thought I was done again, but then I talked to Wise Guy, a pretty knowledgeable modder and homebrew creator who benchmarked a lot of the N64 processes. He's made the homebrew N64 game in the background of this video right now, and he knows a lot more about GCC compiler flex than me. I've realized that stopping GCC from generating jump tables is pretty helpful in the N64 systems. I've told GCC to only do this if there's more than 15 cases, and we had another significant speed up to 13.0 milliseconds. The exception to this is the geo-layout processing functions, where I've turned the whole switch case into a giant funky looking jump table like this. This may look like an awful programming practice, but the speed up was insane, to 12.5 milliseconds, which means that now we could process 80 frames a second. And that is it. We went from 28 milliseconds to 12.5 milliseconds. This new code can process 224% of the geometry that the old one could have. So what is the practical total gain from this? Obviously, just calculating a frame is not enough to also render it. Well, in areas where we had CPU lag, the FPS went up significantly. In the worst case, it went up from 9 FPS to 18 FPS. In this level right here shown, it went up from 22 to 26. I'm overall really happy I managed to pull this whole thing off. It's going to make my job much easier going into the future. Hope you enjoyed this insight into the N64's hardware, and I hope you guys learned a lot. Now we get into the interesting part. I had to optimize the actual code base to make the stuff run faster. I've started with the math functions that are necessary to calculate this graph. As you can see, this function here copies one vector to another vector, and I would not fault you for thinking that this is actually the best way to do it. However, if you do it like this, it compiles into a load and a store. Load, store, load, store. The processor has to wait one cycle to actually have this value ready, which means doing this you waste 3 precious cycles. A more optimal way to do it is this absolutely crazy looking function where you take the value into a variable and then you store it, and you have to declare the variable to be a register. That way it loads, and now the variable is already ready for use, and then it stores it again. I'm gonna show you each type of optimization once and then give you a quick montage of all the functions. So for vec3fset, it sets a vector to a specific value. Again, this seems very straightforward, but in reality doing this is pretty awful because it wastes cycles actually calling the function and loading the arguments. This whole thing would take 8 cycles to execute, when you could also simply have this be an inline function, which makes it take only 3 cycles. It's around 2.5 times faster. Alright, now we're getting into quite crazier territory. The vec3fadd function simply adds a vector to another vector and stores it in the first vector like this. Again, doing this, we have the load operator locking, but there's also another thing that we can optimize quite a bit. So what I suggest doing is something along the lines of this. We have a loop here, which does take more instructions in total. However, the N64 is an instruction cache that saves the last 4000 instructions you've executed. Meaning if you execute a loop 3 times, it doesn't take 3 times as long to execute this as a single loop. It only takes 1.5 times as long, meaning that this takes around 66% of the time that the default example would take. There's some crazy thing going on here, and if you don't understand what this is, I don't blame you, but just trust me, it works. This is the matrix identity function, which generates a matrix that has 0 everywhere except for on the diagonal where it has 1. This is a very good function. However, just storing 1 like this is a huge mistake, because if you look at it, you can simply do it like this, where you store the float representation of the number 1 instead of the actual number 1. Because if you don't do this, then GCC will load the float 1 from RDRAM, which is incredibly slow and takes 2 instruction cycles longer. This is Mario 64's matrix multiplication function, which is a complete disaster. It generates a temporary matrix, it copies back the matrix, it does all of this stuff like line by line, it doesn't use the instruction cache at all, it's just horrid. I've turned it into this crackhead version of the matrix multiplication, which is much faster, but it looks very weird, and if you've ever seen someone program something like this in your company, you'd probably fire him for that, but it is so much faster that it's worth it. The last function I want to talk about is mtxf to mdx. This takes a floating point matrix and turns it into a fixed point matrix. And it goes by all these principles that I mentioned before of using registers and using a loop like this. So it is pretty fast. This function is used so much that it's worth it to do anything you can do to optimize it. So what did I end up doing? I inlined the function. What is this function, you ask? Well, I just rewrote it in assembly. The compiler is not good enough, so we just do it ourselves. This function is quite a bit faster, but I cannot explain you how it works, because explaining assembly is way out of the scope of this video, but it's good.